J.J. Thomson. Okay, so we're getting into more modern history, still a long time ago. 1856 to 1940. He constructed what's called a cathode ray tube. Are you familiar with the old CRT televisions? They're not plasma or flat screen. They had a curved surface. It's a cathode ray tube. It's exactly this thing. And my son likes them to play Super Smash Brothers because there's less of a lag between the controller and the, so you gamers know what I'm talking about. You can find them on the corner. People put them out for free. A cathode ray tube. It's a partially evacuated glass tube. Here's an illustration. There's a little bit of gas in here, and you have two metal electrodes, and you put a high voltage across it. And what happens is you get this ray that goes from the cathode to the anode. The cathode is the negatively charged end, and the anode is the positively charged. They're called cathode rays because they come from the cathode. So he studied these things. Here's an actual photograph. You can see the cathode ray in there. He studied them, and he observed the following properties. The cathode rays travel in straight lines. They are independent of the composition of the material from which they originate. If you make the cathode out of lead, or out of copper, or out of tin, the cathode rays are exactly the same. They carry a negative electrical charge. Electrical charge is a fundamental property of some particles, and it results in attractive and repulsive forces between particles with electrical charge. This is a little summary of what we need to understand about electrical charge. Opposite electrical charges attract each other, like electrical charges repel each other. In this way, electrical charges behave a lot like magnets do. If you've ever played with Brio trains, you know if you get the trains together the wrong way, they won't hook together. You could push them together and they'll pop away. Like charges repel. Opposite charges attract. And these charges have magnitude. And so here, if we get a positive one charge and a negative one charge, they're going to be attracted to each other, and they're going to get together, and then overall, it will have no electrical charge. So Thomson, still playing with his cathode ray tube, he was able to measure the charge to mass ratio of these cathode ray particles by deflecting them with electric and magnetic fields. So here he makes the cathode ray and shoots it over here. We've got a detector here so that you can see where the beam is going. And by applying different electrical and magnetic fields, he could get the ray to bend, and he was able to calculate the charge to mass ratio of that. And the number he came up with was minus 1.76 times 10 to the third coulombs. A coulomb is just a unit of electrical charge per gram of cathode ray particles. So his results implied that the cathode ray particle was about 2,000 times lighter than the lightest known element, hydrogen. He had discovered a particle that was smaller than the indestructible atom. This was big stuff. You could chip off pieces of indestructible atoms. This was the electron that he had discovered. The electron is a negatively charged particle. It has very low mass, and it's present in all atoms. All atoms have electrons in them. That's why the nature of that cathode ray did not depend on the material of the cathode. Because no matter what you made the cathode out of, it's got atoms in it, and every single atom has at least one electron in it. This was the first evidence that elements, the atoms, are formed from the same particles. Now we understand that all atoms are formed from the same basic particles. It's just how they're arranged and how many there are that make them different. Millikan. This was an American physicist. The different branches of science tend to overlap with each other. So Robert Millikan, 1868 to 1953. He did an experiment with oil drops that allowed him to figure out the charge of a single electron. And we're going to watch a little YouTube video on this. It's on the playlist, so for people who are watching this at home, you can go watch this and then come back to the lecture. Okay, so what he did is he made a very fine mist of oil droplets up here. Those oil droplets will, of course, be subject to the law of gravity, and they will fall. Most of them are going to land on this plate and make a big old oily mess. But there is a little tiny hole here, and so droplets that could fall straight down through the hole would continue falling. And he had a microscope set up here and focused on this beam of falling oil droplets so he could measure how fast they were falling. And that's going with the acceleration due to gravity. That's going to help him to get an idea of the mass of the oil droplet. And then he had an ionizing radiation here, X-rays, and so he's bombarding the oil droplets with X-rays, which causes them to become ionized, to develop a charge. Then he applies an electric field across these oil droplets. So here's a positive charge on the top and a negative charge on the bottom. These negatively charged oil droplets are going to be attracted to the positively charged plate above, repelled by the negatively charged plate below. So you have two opposing forces going on. Gravity is pulling them down, and the electric field is pulling them up. We don't need to sit in the dark. Based on the amount of electric field that was needed to get them to stop in midair, he could calculate the charge on the oil droplet. And what he found was that, of course, there were different charges for different oil droplets, but all of those charges were a multiple of that same fundamental charge. So they were all a multiple of minus 1.96 times 10 to the minus 19th coulombs. That's the the charge on one electron. From Thomson's data with the mass to charge ratio, he was able then to calculate the mass of a single electron. Any questions about that experiment? I'm not going to test you on the experiment either, but I think it's helpful to look at some of these and get an idea for how do scientists go about measuring things that are too small to be measured. It's really like a puzzle to figure out what's going on inside this thing. We're measuring the charge on something that's so small that we can't see it, even with a scanning tunneling microscope. Electrons are way smaller even than atoms. So you think about it, and it's really mind-boggling. And this was done in like 1909, 1908. Okay? Most people didn't even have electricity in their houses, right? This was really cool stuff. He was basically shooting X-rays into his face. Yeah, a lot of these early scientists did not have normal life expectancies because they did not understand everything they were dealing with, and they did expose themselves to some dangerous things. So they sacrificed. Heroes. They are heroes. So he had that number, and he had Thomson's mass to charge ratio, and then he was able to calculate the mass of the electron. And the mass of an electron is 9.1 times 10 to the minus 28 grams. That is 0.12. We need to make 27 zeros and then 91 grams. Is that a small number? Heck yeah. We can't even comprehend how small of a number that is. Electrons are really, really small.